Welcome to the Quantopian lecture series. My name is Anthony Ng. I will be your lesson instructor. In 2010, I became a senior lecturer at a local institute of higher learning here in Singapore to pursue my passion, leaving behind the banking industry. I hold a double master's degree, one in MBA from University of Otago and the other Masters of Science in Financial Engineering from National University of Singapore. I help Quantopian conduct algorithmic trading workshops at the introductory as well as the advanced level as well. In this lesson, we're going to cover NumPy. Basically, this lesson is called Introduction to NumPy by Maxwell Magnaut. NumPy really is an incredibly powerful package in Python, basically that is used right throughout the Quantopian platform. It has a strong integration with pandas and other tools that will be covered in the lecture series. NumPy adds support for multi-dimensional arrays and mathematical functions that allow you to easily perform linear algebra calculations. This lecture will be a collection of linear algebra examples computed using NumPy. So the first thing we're going to do is import NumPy as NP, that's the common short form for NumPy. We are also going to import matplotlib. This is really for visualization purpose. This is how you import it, matplotlib.pyplot as plt. So looking at basic NumPy arrays, the most basic way that we could make use of NumPy in finance is calculation of the mean return of a portfolio. Now say that we have a list of, they contain the historical returns of several stocks, which is this one here. Let me just run these cells. In this list, what do we have? We have 1, 2, 3, 4, 5 returns, and we're gonna just store all of these, store this list into stock list. We can make an array by calling a function on the list by storing numpy.array and store this into returns, and then we print the returns out as well as showing what the types. The data types is. So it shows that the returns is same as the list, except this time around the data type is actually a NumPy array. Now you'd notice that the type of array is ND array, not just array. This is because NumPy arrays can be created with multiple dimensions. If we pass np.array, a list of list, it will create a two-dimensional array. If passed a list of a list, it will create a 3D array and so on and so forth. If we store the NumPy array 1, 2, this is a list, this is another list, and 3, 4, and store this NumPy array into A, and we print it out, notice that it's actually a two-dimensional array and the type is a NumPy array. We can access the dimension of an array by looking at its shape member variable, so you just need to print the variable name A and then using a dot method and shape, and you notice that is actually a 2 by 2. Arrays are indexed in much the same way as lists in Python. Elements of a list begin indexing from 0 and end at n-1, where n is the length of the array. Now if we print the returns, bracket 0, so we're indexing the first one, and the returns of the length -1, which is the last one. If we scroll up here, this is the returns. The returns look like this. Basically 0 here is pointing to the first one. Length, which is n, -1 really refers or point to 4.2, so that's why you have the results of 3.5 and 4.2. We can take a slice of an array using a colon, just like a list. So if we print returns from 1 to 3, basically we are pointing to 5 and 2. Right. A slice of an array, like a list, will select a group of elements in the array, starting from the first element indicated and going up to, but not including the last element indicated. It's exactly the same as a list. In the case of multi-dimensional arrays, many of the same conventions with slicing and indexing still hold. We can access the first column of a 2D array like so as well. So since this is a 2D, this basically refers to all of it. Colon means everything, 0 means we are pointing to the first Okay, so if we look at the 1, 2, and 3, 4, which is A, so really we're actually slicing this column here. Okay, this is pointing to the column, and this is pointing to the so-called row itself. So we want all the row and only column number 1. So the way that array, NumPy array, is row first, then column. And the first row of a 2D array, like so, we put down 0, really is first row, and then column, meaning we want all of the contents at that row itself. So remember, this is the row, this is the column. Notice that each slice of the array returns yet another array. So if we print the type of this, we get a NumPy array. Passing only one index to a 2D array will result in returning the row. Okay, so we are only getting back the row within the given index as well, providing us with another way to access individual rows. So that's really A0, meaning we're looking at row number 1. Accessing the index of an individual element will return only the element itself. So A11 will only give us the element itself. Okay, let's look at array functions. Functions built into a NumPy can be easily called on arrays. Most functions are applied to an array element-wise, as scalar multiplication is. For example, if we call log on an array, the algorithm will be taken of each element. So basically, the log functions will be applied to each individual element itself. So when we do a numpy.log function, so this is the array function, so it will actually calculate log for all of these 5 individual elements itself. Some functions return a single value. This is because they treat the array as a collection, similar to a list, performing the designated function. For example, the mean function will do exactly what you expect, calculating the mean of an array. So np.mean basically calculate the mean of all of the returns itself. Or the max will return the maximum element, so you always need to put an np dot in front to calculate the maximum. So for further reading on the universal functions in NumPy, check out the documentation by clicking on this. It will actually point you to the documentation itself. So the next we're going to look at return to the returns. Now let's modify our returns array with scalar values. If we add a scalar value to an array, it will be added to every element of the array. If we multiply an array by a scalar value, it will be multiplied against every element of the array. If we do both will happen. So let's do this. So taking the returns from previously multiplied by 2 plus a scalar value of 5, you notice that it will be multiplied by 2 first and then add 5 to it. NumPy also has functions specifically built to operate on arrays. Let's take the mean and standard deviation of this group of returns. So if we print, basically this is the text mean within the actual apostrophe itself, means colon. So this is the actual calculation itself, numpy.mean of the returns, and again this is the comment, standard deviation, this is the calculation itself, numpy.std returns. That gives you the mean being that and the standard deviation being that. So let's simulate a universe of stocks using NumPy's functions. First, we need to create the array to hold the assets and returns that we will use to build a portfolio. This is because arrays are created with a fixed size. The dimension can't be changed without creating a new array. So here, we are looking at n is equal to 10. Assets is numpy.zeros, n, which is a dimension of 10, comma 100. So basically, we're looking at 10 rows and 100 columns. And the returns, likewise, is 10 rows and 100 columns. The function zeros is a built-in function, creates a NumPy array with the given dimensions that is entirely filled with 0. We can pass a single value or a tuple of as many dimensions as we like. Passing the tuple n, 100 return a 2-dimensional arrays with n rows and 100 columns. Our result is a n times 100 array. Now we will simulate a base asset. We want the universe of stocks to be correlated with each other, so we will use this initial value to generate the others. Okay, so if we take a look at this, this is just the variable name, np.random.normal. Okay, we want to generate 100 random numbers, but it's normally distributed. Okay, so we have, this is the mean, this is the standard deviation, and the returns of this is store basically r_1 itself. The assets is the cumulative products of r_1, which is the variable we created here. Now the random module is in NumPy is exceedingly useful. It contains method for sampling from many probability distributions, some of which are covered in the random variables lecture in the Quantopian series. In this case, we draw n is equal to 100 random samples from a normal distribution with the mean of 1.01 and standard deviation of 0.03. We treat these as the daily percentage returns of our assets and take the cumulative product of these samples to get the current price. Now, the way we have generated our universe, the individual Ri vectors are each one-dimensional arrays, and the returns and assets variables contain 2-dimensional arrays. Above, we set the individual row of both returns and assets to be the first Ri vector and the cumulative assets price based on those returns respectively. We will now use this base asset to create a few other random assets that are correlated with it. Right, so what we're going to do here is that we're going to generate assets that are correlated with the Ri. Okay, so we're going to use a for loop. Okay, so we're going to use R1, okay, which is this asset here. Ri really is a new asset. Okay, and we have random normal distribution. Okay, we're generating another 100 with the mean of that and the standard deviation of that. So in essence, this is to add into this. Okay, and for each one of these, we store it into the returns and index into I. So basically, we have 1 to n, and in this case here is 100. So we're going to generate 100 assets basically with normally distributed assets. So basically we are storing the returns, what we generate here using this formula here. Basically, in essence, by and large, it's based off this. The so-called mean is 1.01, and this is very, very small. So in essence, it's gonna be very, very closely correlated in terms of the returns. It's just shifted up by a little bit, which is by 1%, well, 0.1% really, and the standard deviation is fairly high, so it's going to fluctuate around. So in essence, we are actually generating the returns, 100 of them, based on this n, and just going to keep repeating it and store all of this into the assets itself as well. This is the cumulative product of it. So the mean returns will be calculated for the whole R. So first of all, we calculate the returns, okay, mean returns of R, and then minus 1 multiplied by 100 for R in returns. So what does this mean? This is actually what you call a list comprehension. So we have returns. Okay, what is returns? That's this one here. So we are going through and extracting them out one by one. And then for each one, which is this one here, remember each R has 100 returns. Okay, it was generated from here and is stored into this. So each and every single row has 100. We calculate the mean, minus it by 1, and then multiply by 100. So in essence, this is really calculating the actual percentage returns. And the return volatility really is the same way, just calculating the standard deviation using the NumPy. So in summary, here we generate the remaining A-1 as securities that we want in our universe by adding random noise, which is R1, this one here. This ensures that our N-1 other assets will be correlated with the base assets because they have same or have some underlying information that is shared. Let's plot the mean returns of each assets and see what it looks like. So we are plotting the returns, And we let X label the X-axis as stock, Y label as the returns, and we print the title for how many random assets. So when this is printed out, okay, what you can see here is the returns fluctuates from around 0.3 all the way to 0.8 something. Okay. Calculating the expected returns. So now we have a universe of stocks. Excellent. Now let's put them together in a portfolio and calculate its expected return and risk. We will start off by generating n random weights for each assets in our portfolio. Okay, how do we do that? We use the random generator by drawing from a uniform distribution, and the weights is all stored here. Okay, so these are all random uniform numbers, except that we're gonna weight them by the sum of all the weights itself. So in order to basically make the weights add up to 100%, we take the weights which was generated here and we divide it by the total of it. So we have to rescale the weights so that they all add up to 1. Basically, that's what this is. This second line is. Add up to 1, we do this by scaling the weights vector by the sum total of all the weights. This step ensures that we will be using 100% of the portfolio's cash. To calculate the mean return of the portfolio, we have to scale each asset's return by designated weight. We can pull each element of each array and multiply them individually. But it's quicker to use NumPy's linear algebra methods. The function we want is dot. This will calculate the dot product between two arrays for us. So V is equal to 1, 2, 3, and W is equal to 4, 5, 6. Then what you have is 1 multiplied by 4, 2 by 5, 3 by 6. So this is what I mean by dot product. For a one-dimensional vector, the dot product will multiply each element pointwise and add all the products together. In this case, we have a vector of weights, W1, W2, all the way to Wn, and a vector of returns. This is mu, or mean returns, mu1, mu2, all the way to n. If we take the dot product, basically what we get is something that's really similar to this. Weight 1 multiplied by mu1, weight 2 multiplied by mu2, so just add them up. So this is the sum of it, which is mu of the portfolio itself, or the mean return of the portfolio itself. This uses the sum of all the assets returns scaled by the respective weights. This is the portfolio's overall expected returns. So in essence, this is the line, this is the explanation, this is the actual execution of it. A lot shorter than the write-up, I can assure you. So if you print the expected returns of the portfolio, which is really this one here, you get the returns of the expected returns of the portfolio is 0.5073. Now don't worry if your notebook, which you clone from the directly from the lecture series, is different from mine, because I restarted my notebook, reran it. So that's why the expected return is different. Every time you run it, it's different. The reason being we have a random number generation here and before, hence the result is different. So calculating the mean return is fairly intuitive and does not require too much explanation of linear algebra. However, calculation of the variance of the portfolio require a little bit more background, which we will dig into right now. The first thing that we need to do, though, we need to cover some basics with regards to how NumPy works. We need to be aware of not a number. That's what nan means. Okay, not your nana. It's just not a number. Most of the time, all of these calculations will work without an issue. However, when working with real data, we run the risk of having not a number values in our arrays. This is NumPy's way of saying that the data there is missing or doesn't exist. These NaN values can lead to errors in mathematical calculations, so it is important to be aware of whether your array contains NaN values and to know how to drop them. So take this, we store this into the variable v, NumPy array 1, 2, we purposely create another number here, and 4, 5. So if you print it out, this is what it looks like. Let's see what happens when we try to make the mean of this array, and notice that it gives you another number. Clearly, NaN value can have a large impact on our calculation. Fortunately, we can check for NaN values with the isNaN function. So numpy.isNaN bracket the actual variable itself, and what you get is false, false, true, false, false, and the data type is Boolean. Calling isNan on an array will call the function on each value of the array, returning a value of true if the element is nan, and false if the element is valid. Now, knowing whether your array contains nan values is all good and well, but what do we do with them? Or how do we remove it? Good thing is, NumPy arrays can be indexed by Boolean values, true or false. If we use a Boolean array to index an array, we will remove all values of the array that register as false under the condition. We use the isNan function in creating a Boolean array, assigning a true value to everything that is not nan and a false to the nans, and we use them to index the same array. So in essence, that really is saying if it's nan, we give it a true, which is here. Except that we have this notation here which inverts the Boolean. Okay, and we store these into ix, which is the index. So if we print all of these, we will get 1, 2, 4, 5. These will point us to the not nan. Okay, so if we print the NumPy mean of v, except that we are indexing only those which is not nan, we will get a mean value of 3. Now, there are a few shortcuts to this process in the form of NumPy functions specifically built in to handle them, such as nanMean, which will actually do exactly what we did there. The nanMeans function simply calculates the mean of the array as if there's no nan values at all. There are a few more of these functions, so feel free to read more about them in documentation. These indeterminate values are more an issue with data than linear algebra itself, so it is helpful that there are ways to handle them. Okay, the conclusion here. Linear algebra is really very pervasive in finance and in general. For example, the calculation of optimal weights according to modern portfolio theory is done using linear algebra techniques. The arrays and functions NumPy allow us to handle these calculations in a very intuitive way. For a quick intro into linear algebra and how to use NumPy to do more significant matrix calculations, proceed to the next section. This is what we're going to touch on, okay, including the calculation of the variance itself. So let's dig into linear algebra, albeit very briefly. So let's start with some basic overview of some linear algebra. Now, linear algebra comes down to the multiplication and composition of scalar and matrix value. A scalar value is just a real number that we multiply against an array. When we scale a matrix or array using a scalar, we multiply each individual element of that matrix or array by the scalar. A matrix is a collection of values typically represented by m times n grid, where m is the number of rows and n is the number of columns. So again, row columns, okay, in that sequence. The edge length m and n do not necessarily have to be different. If we have m equals to n, we call this a square matrix. A particularly interesting case of matrix is when m is equal to 1 or n is equal to 1. In this case, we have a special case of a matrix which we call vector. While there is a matrix object in NumPy, we will be doing everything using NumPy arrays because they can have dimensions greater than 2. For the purpose of this section, we will be using matrix and array interchangeably. We can express matrix equation as y is equal to a multiplied by x, where a is a m times n matrix, y is a m times 1 vector, and x is the n times 1 vector. Hopefully you remember some of these from high school. In order for you to have a be able to multiply n, the second one, okay, this is row, this is column. The column of the first one must equals to the row of the second one. On the right hand side of the equation, we are multiplying a matrix by a vector. This requires a little bit more clarification, lest we think that we can go about multiplying any matrix by any other matrices. So let's dig into this. Okay, matrix multiplication. With matrix multiplication, the order in which the matrices are multiplied matters a lot. Multiplying a matrix on the left side by another matrix may be just fine, but multiplying on the right may be undefined. So here we are creating two matrices, A and B. Notice their different dimension. A dimension is 3 by 5, 3 rows by 5 columns. B is 4 times 3. The general rule of what we can and cannot be multiplied into which order is based on the dimension of the matrices. Specifically, the number of columns columns in the matrix on the left must be equal to the number of rows in the matrix on the right. So let me repeat this again. The number of columns in the matrix on the left must be equal to the number of rows in the matrix on the right. In super informal terms, let's just say we have a M times N matrix and P times Q matrix. If we multiply the first by the second on the right, we get the following. M times N, the left one, P times Q, the right one. So what we get, assuming N is equal to P, we get M times Q dimension. So the resultant product has the same number of rows as the left matrix and the same number of columns as the right matrix. This limitation of matrix multiplication with regards to dimension is important to keep track of when writing code, otherwise you're going to get error everywhere. To demonstrate this, we use the dot function to multiply our matrices below. So if we multiply A by B, okay, notice it's 3 by 5 and 4 by 3. 5 is not equals to 4, you're going to get an error. And this is exactly what we've got. 3 by 5 and 4 by 3 is not aligned. 5 dimension is not equals to 4. All right, we know that. Okay, so this results make sense in accordance to our rule. Multiplying a 3 by 5 matrix on the right by a 4 by 3 matrix results in an error, while multiplying a 4 by 3 matrix on the right by a 3 by 5 matrix result in a 4 by 3. So hence what we need to do, okay, is to rearrange this a little bit. B, if we recall, we just need to pull this down. B is 4 by 3, A is 3 by 5. So here now we have 3 is equal to 3. We will get 5 by 4, which is exactly what we get here. Sorry, 4 by 5, the other way around. B multiplies by A. Right, having done that, let's move on to the actual finance itself, which is portfolio variance. Let's return to our portfolio example from before. We calculate the expected return of the portfolio, but how do we calculate the variance? We start by trying to evaluate the portfolio as the sum of each individual assets scaled by its weight. Now, this is variance, okay, portfolio variance. Variance is the square of standard deviation. So if we take a look at the variance of portfolio, it's equal to the variance of the individual assets itself. Okay, so you apply the variance function into all of these, okay, individual asset itself. So S0 to Sn are the assets contained within our universe. If all of our assets were independent of each other, we could simply evaluate this, which is these here. And what you get is basically weight 1 multiplied by the variance, weight 2 multiplied by the variance, all the way to weight n multiplied by the nth asset's variance. However, there's always a however in finance. That's the beauty of it. All of our assets depend on each other by their constructions. Remember, when we were constructing, they are correlated, and in real world is exactly the same. They are correlated in some way. They are all in some way related to our base assets and therefore each other. We thus have to calculate the variance of the portfolio by including the individual pairwise covariance of each asset. Our formula for the variance of the portfolio is basically this beautiful notation here. So you have individual portfolios, let me repeat, individual assets weight multiplied by its variance, and also the actual covariance of all of the assets to each other. So you have this P, or this row, really, this row ij is the correlation between asset I and asset j. Okay, so correlation coefficient really is covariance divided by the standard deviation of each asset. This seems exceedingly complicated, but we can easily handle all of this with NumPy by using NumPy arrays. Rather than going into the details of how to derive that, that's not the point of this exercise. Just remember, this is how you calculate the variance, and we just use a NumPy array to calculate this. So first we calculate the covariance matrix that relates all of the individual stocks in our universe. Let's go into the code itself. How do we calculate the covariance? We thankfully have a NumPy function called numpy.cov, which is NumPy covariance of the returns. And when we calculate the actual matrix itself and print it out, and here you have the actual covariance matrix itself. The array is not formatted particularly nicely, but a covariance matrix is a very important concept. The covariance matrix is basically of this form. The diagonal is really the variance of the individual asset itself. The rest are the covariance itself. So each diagonal entry is the variance of the asset at that index, and each off diagonal holds the covariance of two assets indexed by the column and row number. What is important is that once we have the covariance matrix, we are able to do some very quick linear algebra to calculate the variance of overall portfolio. We can represent the variance of the portfolio in array form as using this. Okay, the weight multiplied by the covariance matrix multiplied by the transposed weight itself, where C is the covariance matrix of all the assets and W is the array containing the weights of each individual assets. The superscript T on the second W listed above denotes the transpose of W. For reference on the evaluation of variance of a portfolio as a matrix equation, best go to Wikipedia. The transpose of an array is what you get when you switch the rows and columns of an array. This has the effect of reflecting an array across what you might imagine as a diagonal. For example, take our array A from above. If we print A, this is what it looked like. It's a 3 by 5. The transpose looked like a mirror image. So in essence, now it's 1, 2, 3, 12, 6 down this way, 4, 5, 6, 15 down this way. So it's basically transposing. This is what you mean by transposing. It went from 3 by 5 to 5 by 3. But weight here is a one-dimensional array, a vector. It makes perfect sense to take the transpose of a 3 by 5 array, so the output will be a 5 by 3 array. But a one-dimensional array is not quite as intuitive. A typical one-dimensional array can be thought of as 1 times n horizontal vector. Thus, taking the transpose of this array essentially means changing it to a n times 1 vertical vector. This makes sense because one-dimensional arrays are still arrays, and any multiplication done between 1D and higher dimensional arrays must keep in line with our dimensionality issue of matrix multiplication. Right, I think I blah 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 for quite long. So to make a long story short, we think of weight as 1 times n since we have n securities. That makes it so that weight transpose is n times 1. Again, our covariance matrix is n times n, so the overall multiplication works out like so. In informal terms, this is what it looks like. It becomes 1 by 1. 1 times n multiplied by n times n. Remember, this matches, so it becomes 1 times n multiplied by this, and these two are the same, so matches, so ended up taking 1 and 1. It becomes one number overall. Multiplying the covariance matrix on the left by the plain horizontal vector, on the right by the vectors transpose, results in the calculation of a single scalar value, our portfolio's variance. So knowing this, let's proceed and calculate the portfolio variance. We can easily calculate the product of these arrays by using dot for matrix multiplication, though this time we have to do it twice. So variance, within it, we have the weights times the covariance matrix, and then we have a NumPy dot multiplication of the result of this, which is this part here, multiplied by the external, which is this one here, and what you get is the actual variance of the portfolio. If you want to calculate the volatility or the standard deviation, you take a square root of that, and when you print the volatility, it gives you 0.03. So all of this might not make sense at first glance. It helps to go back and forth between the theory and the code representations until you have a better grasp of the mathematics involved. It is definitely not necessary to be an expert on linear algebra and on matrix operations, but linear algebra can help to streamline the process of working with large amounts of data. So for further reading on NumPy, check out the documentations. Once again, as always, thank you so much for listening and paying attention. I look forward to catching up with you in the next lesson.